Alrighty, so just to remind you where we were in the last lecture, we were implementing a linked list, and we got to the remove method. And so remember to remove an element from a list. So here I want to remove the element shown in blue. If you're in a linked list, you have to adjust the length of the node in front of the one that you want to remove. And so you actually want to move to the node in front of the element where you're removing it. And so when you remove the element, there's a sequence of steps that you have to take. I'm just going to skip over the slides. If you follow the pictures in the slides, you can implement the remove method fairly easily. What I wanted to remind you of, though, is that we created this method called remove after inside our class that removes the node after some specified node. Right? And the reason we're doing this is because when we implement the iterator, it's very handy to have the remove after method so that the iterator can remove a node from the sequence. And so that's what I want to talk about today. So this is the lecture set 32. So when you implement an iterator for a linked list, it's similar to implementing an iterator for an array-based list. The implementation, though, looks very different. So conceptually, it's the same thing. The implementation is very different. So remember that your iterator sits between elements. So here I've got an iterator sitting between the elements C and D. Right? In our array-based implementation, we kept track of that index and that index. In a linked sequence of nodes, though, it doesn't really make sense to keep track of indexes because the indexes aren't useful. Right? If you kept track of the indexes, then every time you want to move to a node at a specific index, you would have to traverse the sequence of nodes, which is inefficient. So instead, what we want to do is we want to keep track of some nodes. And it's not immediately obvious which nodes you want to keep track of. You might think that if you were to replicate the implementation from the array list, you would keep track of that node and that node. But it turns out that's not the case. So for this iterator here, the way that we got here was that we called next a few times. So our iterator starts out here, we called next, return the A, you call next again, you return the B, you return next, and we returned the second here. Previous, yes, all right, and so here, the node, the last element that was returned was the C. So the element returned by the most recent call to next is in the node that's immediately in front of the iterator. So it looks like we want to keep track of that node for sure. I guess the thing to realize is that if you're keeping track of this node, you don't actually want to keep track of the next node because you can always get to the next node by following that link there. So we want to keep track of this node here, and it turns out we want to keep track of the node in front of it as well. Okay. So we're going to use the field previous to refer to the element returned by the most recent call to next. Right. So the iterator got here by returning the C. Right. If you're going to call next again, it's going to return the D, and the iterator will move again. So if we're keeping track of this node here, right? If you want to remove that node, so if you want to implement the remove method for the iterator, you actually need the node in front of it in order to remove the previous node. And so it turns out we're also going to keep track of the node in front of previous. Right? So the two nodes that we're keeping track of are these two here. So previous, the element most returned, points at the node containing the element last returned by next. Right? And previous is just the element or the node in front of previous. And the reason we're keeping track of previous is because to remove the element last returned by next, we need the node in front of it. All right, so what does our iterator class look like? So inside the linked list class, you're going to make a an inner class called LL iterator, so linked list iterator. It implements the iterator interface, so it has next, and remove. Right, our two fields are previous, right, and previous, right. So again, the node holding the element right before the iterator, right, and the node immediately in front of previous. So for our constructor, so this starts the iterator at the front of the linked list. So we're going to do something funny here. We're going to make a new node, which seems strange, right? So I'm going to actually make a new node in the constructor, and I'm going to set previous to null, right? So this line right here is funny. So we're going to make a new node. It's going to hold no element, right? And it's going to be pointing at the head node of the linked list. And this looks really strange, right? So what's going on here? So at the start of the iteration, there is no node for previous to refer to, right? So remember, previous holds previous points at the node containing the element last returned by next. So there is no element last returned by next when you start out at the beginning of the list. And so if I didn't do this right here, instead we'd end up setting previous to null, right? Previous would also be null. Now, the unfortunate thing with setting previous to null is that in all of your methods, you're going to have to pay attention to whether or not previous is equal to null, which is going to be awkward, and I don't want to deal with that case, right? So I don't want to deal with any special cases. So I would like there to be the invariant that our field previous is never null, right? So in other words, it always points at something. And so the trick that you play is you insert a dummy node. So the iterator constructor inserts this node that's not used for anything other than to ensure that previous is never null. Right. And so this node here is called a sentinel node. So you can implement a linked list using sentinel nodes at the front and the back of the list. Right. So what that lets you do is that you never have to worry about the special cases where there is no head node and there is no tail node. Right? If you insert a pair of sentinel nodes at the front and the back, then you're never in the situation where there are no nodes in your list. Right? So in other words, your empty list has a front sentinel node and a back sentinel node and nothing in between. And so in many linked list implementations, you'll see the use of sentinel nodes for that reason. So here I'm going to use a sentinel node at the front, and that makes implementing the iterator a little bit easier. And of course, previous can always be null, so there's no issue with that. So when we make a new iterator, we're always creating a new sentinel node in front of the head node, which is what that line of code does right there. Notice that the linked list itself never knows that this sentinel node exists, right? So if you go back and look at the linked list implementation, all that it has is a reference to the head node, right? It never knows that there's a node in front of it. Okay, so now when you go to implement your methods, it's relatively easy. So has next returns true if there are still some elements to look at in the list, right? So how do you know that there's still some elements to look at in the list? So remember, we're keeping track of previous, right? So if previous next points at something, there's still elements to look at in the list, right? So here, because we have a sentinel node, right? Previous next points at the head node. So we know that there's some elements to look at still, so has next returns true. Right? When you get to the end of the list, right, our previous node is now the tail node, and so previous next is null. So we know that there are no more elements to look at. So has next is dead easy to implement as long as previous isn't null. Right? If previous is null, you need a separate if statement to take care of the special case where it is null. Right? Because if you use null to try to access next, you get a null pointer exception. So has next is just one line. As long as previous next points at something, there's something else to look at in the list. Okay, so what about next? So next simply moves the iterator one position to the right, and it returns the element sitting in previous. So, sorry. So if our iterator is here, right, you call next, it moves over one position, right? Previous moves over one position, previous moves over one position, right? You return the element sitting in previous. So it's easy to implement as well, right? First, check, are there any elements to look at? If there isn't, throw an exception. Remember, it's always no such element exception for the iterator. Now advance previous, previous, and previous one position to the right. You have to be a little bit careful when you update previous, previous, right? So you don't want to write this previous, previous equals this previous, previous dot next. And you'll see why in a moment. Right? So instead, you want to set it to equal this previous. Right? For previous, you can update it so that it's equal to previous dot next. Again, this is easy to do because, and it's safe. It's always safe to do because previous is never null. So you know that that's never null. So you know that its next one always exists. So that's nice. I don't have an if statement here checking whether or not it's null, and then simply return the element sitting in the new node pointed at by previous. So next is also easy to implement. Okay, so what about remove? So remove is supposed to remove the element last returned by next. So in other words, we want to remove the element sitting in previous, which means for a linked list, we want to remove the node pointed at by previous. Right? This would be awkward to do if we didn't have a method remove after inside linked list. Right? So because we have this method, it's easy to implement remove for the iterator. If you don't have this method inside linked list, then you're stuck iterating over the sequence of nodes until you get to previous, previous. Right? And then your remove method for the iterator now becomes on, right? Because you have to move over a bunch of nodes to get to the node that you want to move. Right? Because we have remove after, right? Our remove method for the iterator is in O1, which is nice. So this is another one of the situations where you would prefer a linked list over an array-based list. Right? In an array-based list, if you remove from the middle of the list, it's always in ON. Right? So even if if you're iterating over the sequence of over the elements of an array-based list and removing stuff as you go, every time you remove something, that's an ON operation. So that's which is relatively slow. If you're iterating over the sequence of elements in a linked list and removing stuff as you go, right? Each remove operation is in O1. Which is nice, right? So this is one of the times when you might consider a linked list over an array list, right? Is if one of the operations that you're frequently doing is iterating over the list and removing stuff as you go. So to implement remove is straightforward in this case, right? Or actually removing the element is easy because we have remove after. When you remove an element, so when I remove that C from the sequence, the picture that you end up with is this, right? So you remove the node, previous now no longer points at anything because we just got rid of the node that it was pointing at. We need to make sure that previous refers to the node immediately in front of the iterator, right? So in other words, I need to make sure that previous actually points at the B now, right? But that's easy to do. I have a reference to that node. It's just previous, previous, right? So I can set previous to equal previous, previous, right? And now I set previous, previous to be equal to null, right? I set it to null to indicate that we've called remove once for the most recent call to next. If you thought that maybe you wanted to set previous, previous to the node in front, you can't do that you can't do that efficiently anyway in a singly linked list, right? If I'm at B, there's no way for me to get to A efficiently. I have to start at the front of the list and then move to that node. So by assigning previous, previous to null, that lets us know we've called remove already and we shouldn't call it again. Or if we try to call it again, we throw an exception. Okay, now remember we got this sentinel node sitting in the front, right? So there's our sentinel node in the front of our linked list, right? So the question is if I remove the first element of the list, does our sentinel node stay intact, right? And the answer is it does, in fact, stay intact, right? So if next has been called exactly once, right, then we're sitting between the first and second element of the list, right? If I call remove, right, remove front causes the list to adjust the field head so that it refers to the second element of the list, right? So our list, so if I call remove front on this thing here, right? Head now points at B, right? Previous still refers to the old head node. Okay. Previous still refers to the sentinel node. So what I would like to do is I would like to remove the element sitting in the node that we just removed, right? Which converts that node to a sentinel node now, right? And so our linked list still has a sentinel node sitting in the front, which is nice, right? All of our other methods that assume that previous is never null still work, right? And away you go. So what does it look like? Check if previous is null, right? If it is, we've already removed the element last returned by next, or we haven't called next yet. So we're not allowed to call remove, so throw an exception, right? If previous is equal to the head node of the linked list, right, then I would like to call remove front instead of calling remove after, right? So that removes the front node of the list for us. Okay. And then null out the element sitting in the previous node. That converts the node to a sentinel node. Otherwise, call remove after using previous, right? And then set this previous to equal previous. Right? And in any case, right, always set previous to null to indicate that remove has been called. And there's your linked list iterator. So it's conceptually it's the same as with an array-based list, but the implementation is very different because you're using nodes instead of indexes. All right, any questions about the linked list iterators? So I never actually asked you to implement one of these things on the exam. It's too hard for the purposes of the exam. So the only questions you might see with the iterators are conceptual type questions, right? So don't bother memorizing the implementation or anything like that, but have an idea of how they actually work, right? And what an iterator is. Speaking of the exam, there is an exam, of course. I think the lecture slides that are posted on OnQ are for an old version of this course. It's not even this course. I think it's for SISC 124. So the exam date is wrong. It's like from 2021 or something like that. And I think this slide has some differences on it as well. Okay, so for the purpose of this course, I always get asked what's on the exam. Tell people that the exam is not comprehensive, right? But the problem with this course is that this course builds from day one all the way to the last day in the course, right? If you don't understand the material earlier in the course, you're going to have a lot of trouble at this point in the course, right? So you need to be familiar with all the course material, right? But I'm not actually asking you about all the course material, right? So in other words, anything that was tested previously, I'm not going to ask you about it again, right? Which means I'm not going to ask you to cook up a class that does something relatively straightforward again from scratch, right? So instead, the exam topics cover mostly cover the stuff from part 3 and part 4 of the course, right? So the relationship between classes and generics and data structures, part 4 of the course. Your third test next week also covers part 3, right? And I'll post an announcement and a sample quiz or sample test for you today or tomorrow for the test. But for the exam, it's not comprehensive, right? So it's only going to cover the stuff that you are not previously tested on. And again, some stuff from part 3 of the course, right? So primarily inheritance and the generics part of the course are covered by the exam. Any questions about the exam? The exam's only 2 hours long, so it's not a full 3-hour exam. Yes.
It's only 50%, right?
I forget exactly what it is. I think so. I believe so. But you can, I guess we can look on OnQ to actually check. Content. Yeah, they're all 15%. Okay, so I think the second last set of slides are 33. Okay, so going back to generics. Okay, so there's something funny on when we were talking about generic methods. Some of the slides had question marks on them, right? So there were these methods where you specify the type for I guess a stack and a collection. And there's this question mark whether the types had to be exactly the same, right? And it turns out in all those cases, the answer is no, they don't have to be exactly the same. And that's because of inheritance. And so when you're implementing generics, you don't have to remember that inheritance exists, but it's nice if you do remember that it exists, right? Because that lets you make methods that are methods and classes that are more flexible in the face of inheritance, right? So this is specifying type requirements in generic classes and methods. So hopefully at some point someone told you about sorting, right? So sorting is probably one of the most fundamental algorithmic problems that are studied by computing science students. There's many types of sorting algorithms, right? If you have a sorted collection, there are algorithms that work on these things too, right? So like binary search only works properly if you have a sorted list or array. Right? A bunch of data structures assume something about the sorting of the elements, right? You can have sorted sets, you can have sorted maps, you can have sorted trees, right? Priority queues are queues where the elements are sorted by their priority, right? And so on and so on and so on and so on, right? This idea of order or sorting turns out to be very important in computing science. Okay, so when you sort stuff, the standard way, or I guess the generic way of sorting stuff depends on a particular mathematical operation, right? So when you want to sort something, the standard sorting algorithms do a comparison, right? Is this element less than another element, or is this element greater than another element, right? So the basic mathematical operation required by most sorting algorithms is comparison. And the sorting algorithms that work this way are called comparison-based sorting algorithms. So if you make a generic sorted collection, or if you create a generic method, right, is there a way where you can specify that the element type supports a comparison of some kind, right? The answer is yes, you can, right? And so the way you do this with Java generics is you use what's called a bounded type parameter, right? So we've seen type parameters already. T or E, right? It's just the name. It's just a name that stands in for the actual type. It turns out that you can put constraints on these types. So a bounded type parameter is used when you need to restrict the types that can be used for a generic type parameter, right? So in other words, you have a method or a class that's generic, but the type has to meet certain requirements. So the way you do this is well, the language recycles extends, unfortunately. So we're going to reuse the extends keyword after the type parameter, and then you specify what's called its upper bound. Right. So an upper bound can be a class that the type is a descendant of. There should be an F here, sorry. Or it can be an interface that the type implements. So what the heck does that look like? All right, so remember our point2 class, right? So we created a class that represents a two-dimensional point. Internally, it had an X and a Y coordinate of type double, right? If you wanted to, you can change point2 so that it was a generic type. Now the type of your X and Y coordinates has to be some sort of numeric type. So how do we specify that? Right. So step one, make the class generic. So after the name point2, you put in your type variable. Right? You change the type of X and Y to T. Right. And now we would like to restrict T so that it must be some subclass or some descendant of number. So in the Java language, there's this class called big N number. It turns out it's the superclass of integer, double, float, short character, and what are all the other numeric wrapper types. Right. So by saying T extends number, this places an upper bound on T, right? So the upper bound is number, which means T has to be a subclass of number. can be a descendant class. It doesn't have to be a direct subclass. Right. So now T can be, it can be number, it can be integer, it can be long, it can be short, it can be double, and so on and so on and so on. So let's look at another example. Suppose you wanted to implement a map, right? And you want the map to be sorted. You can do the same thing for a set or a list, right? Sorted list, sorted set, right? There is a restriction on the element type. So for a sorted map, you want your keys to be comparable, right? I want to be able to sort the map using its keys, right? How do you do that? I have to make sure that the key has a compare to method, right? The same thing would happen for a sorted set, right? Sorted set of elements, you need to make sure that the elements are comparable. Sorted list, you need to make sure that the elements are comparable. Right? So how do you do that? So in this case, a mini map is a map that has a fixed capacity, right? So it can't change itself. It cannot increase in capacity, holds a fixed number of elements. Okay, so to restrict the key type so that only types that can be compared are allowed, you impose an upper bound, right? So now K extends, right? Now you want to specify the interface that lets you compare stuff in Java, right? So that's the comparable interface, right? That interface is itself generic, right? So here you want to make sure that your key type implements comparable for the key type K. Right. All that means is that your type has a compare to method. Compare to does what compare to does, right? It lets you compare two values or two elements of type K. Generic methods can also have their own, can also have bounded type parameters. Right? So here's a method that takes in an array and it takes in an element, both of, so the element type for the array is T, right? And the element that you are looking at, or the element that you're using to compare to is also of type T. Right. Now remember I said that there are no generic arrays, right? All that means is that you can't actually make a generic array, right? You can still, so you can't make a new generic array using a generic type. However, you can still have, you can still write a method that operates on arrays of any type T. You just can't make an array of type T, of element type T here. So this method here counts the number of elements in that array that are bigger than elem, right? What do? You write a loop, right, over your array, and you want to write, right? If the element E from the array is greater than elem, add 1 to the count. That doesn't work, right? Why doesn't it work? Because this thing here has type T, it's a reference type, right? Greater than doesn't work for reference types. Right? So what do you need to do? You need to make sure that instead of using greater than, you want to use compare to, right? If you want to use compare to, you have to say that T, you have to impose the constraint that T implements comparable. Right. So how do you do that? Impose the upper bound on T, right? So T extends comparable T. Change the greater than to use compare to instead. Right. So if E compared to elem is greater than 0, if E is greater than elem, right, add 1 to the count. And so this is what tree set and tree map does internally. Right. So if you look at the code inside tree set and tree map, you'll see that there is a compare to, a call to compare to anytime it needs to search or insert an element. Okay, so there's something funny about the way generics behave in in inheritance. Okay, so remember I told you that generics are invariant, right? So here you have object and string. So we know that string is a descendant class of object, right? String is a subtype of is a subclass of object. If you have a list of object and a list of string, though, there is no relationship between them, right? So list of string is not a subclass of list of object. Right? And that prevents, so that means you can't write code that looks like this, right? So you can't make a list of strings and store that in a list of objects. So the reason for doing this is because you end up in all sorts of funny problems if this was allowed to happen. right? It's the same problem that you run into when you work with arrays, right? So suppose that list of string was a subtype of list of object, right? Then you can make a list of strings, right? You can store a reference to that list in a list of objects, right? Now, as far as the compiler is concerned, OBJS is a list of object, right? What can you store in a list of object? You can store anything that you want in a list of object, right? So you could make a date object and store that in the list, right? This would compile if list of string was a subtype of list of object, right? So that would compile, and then you'd run into a problem when you went into the list, got the first element, it's a date, right? And you tried to store that back in a string variable, right? And so this was the exact same situation that happens with arrays, right? And this does happen with arrays in Java. Right? So the designers of the language decided that this is a bad thing, shouldn't let this happen with generic types. And so a list of string is not a list of object. All right. Now, what happens now if you extend a generic class? Right. So here, if I have a class called abstract minimap, right, and I extend that class, so I create a class called sorted minimap, like this, right, you do end up with a subclass. Right? So sorted minimap is a subclass of abstract minimap. Right? The difference here is that your types are generic, whereas here they are not. Right? So here you have a list of string. List of string is not a list of object. Right? Here you've got a sorted minimap that's got some generic types K and B. Right? It is a subclass of abstract minimap, which also has types K and B. Right? So you can extend a generic class, right? But if you have a particular class that, if you have a class, you have a object or a class where the type is actually specified, there's no inheritance relationship here. Right. Similarly, if you extend a generic interface, you create a new subtype, a new sub interface. Right. So if you have an interface called set that's generic, right, and you extend that interface, right, you end up creating a sub interface of set. Right. So sorted set is a set in this case. Right. So there's an example of extending an interface, which I don't think we've seen yet in this course. Right. But you can extend an interface. It works the same way as extending a class. Right. So sorted set has every method that's defined in the set interface. Right. And it can add its own methods as well. So if a class implements a generic interface, then you have to create a subtype. Right. So if you make a tree set, right, and it implements sorted set, right, then a tree set is a sorted set. Right. So you can make a tree set over here, store it in a tree set variable. Right. You can make a sorted set variable over here, and you can store a reference to tree in that variable. Right. So tree set is a sorted set, so you can store tree in sorted. Right. Similarly, sorted set extends the set interface. Right. So all sets, so tree set to tree can also be stored in a variable of type set, and that works as well. Right. And then finally, set extends the collection interface. So you can take tree and store it in a variable COLL, whose type is collection. Right, so those all work as well. All right, so when you're specifying or when you're constraining your generic types, there are times when you actually don't care what the type is. And so there is this wildcard type called the question mark. And you'll see this, that it's used a lot in the standard library. Right? So the question mark is called the wildcard type. You can use it in generic code to indicate that the type is either unknown or you don't care what it is. Right? So when you use it on its own, is called an unbounded wildcard, right? So on its own, it just means, look, I don't care what the type is. So one use of this thing, you might wonder, when would you ever write this, right? So one of the uses is when you have a generic method and your type doesn't actually matter. So remember back to that stacks example, that stacks class, where we had a method called clear, right? Originally, clear was a generic method, right? So the original version of clear was stack and then t, right? In front of the void, we had the generic type t. When you look inside the method, nowhere is the type t ever mentioned, right? So in this particular case, the actual type of the element in stack doesn't matter, right? So instead of writing it as a generic method, you can write it using a wildcard, an unbounded wildcard, right? So stack question mark means you've got a stack of some element type, and I don't care what the element type is, right? It's never used, right? So you could write clear that way instead, right? Whether you choose to write it with a generic type or not. So if you want to write it as stack t and stick the generic type in front, is up to you as the programmer, right? The advice given by the people who created the language is that if you don't care what the generic type is, use the question mark, right? But both are correct, and both methods work exactly the way you want them to. So there's an example of using the question mark on its own. Another use of the unbounded question mark is a generic method where the only methods you need to use are in object. Right? This is acceptable because every reference type in Java is a subtype of object. Right? So if you're only using the methods in object, you can just specify the type as question mark. Right? So clear and print. So I'd like to clear my stack, right? And then print the elements as I'm clearing them, as I'm popping them off the stack. Right. So again, I don't care what the element type is for the stack. Right. I don't need to use the type anywhere here. Right. Because when I pop the stack, I can store the element in a variable of type big O object. Right. So I don't actually need to know what type the element is here. Right. So instead I use object here. This is fine as long as the only thing I'm doing is, in this case, printing the element. Right. So I can send O to print line. Print line ends up calling toString on O. You get the and now you get the string version of whatever this object happens to be. Right. So there's another example of when you can use an unbounded wildcard instead of writing the method generically. Right. So instead, you could write it with a T here and then angle brackets T in front of the void. Right. But because we don't actually care about the type, question mark is acceptable here as well. All right, upper bounded wildcards. So an upper bounded wildcard, which we saw already, right? So the example where our type extended number or where the type extends comparable are all examples of upper bounded wildcards. Right? So this is useful when you want to relax the requirements on a type parameter. Right? So consider the following method that works only if passed a list of numbers. So here I have a method called sum of. It's going to compute the sum of the values in t. Right now, t. This says that it must be a list of number. Okay. So if I iterate over this list, right, the elements in the list are of type big N number. Turns out, if you look at the documentation for number, there's a method called double value that gives you the value of the number as a double value. Right, so that lets me compute the sum as a double value. Okay, so what's the problem? So remember what the problem is here, right? So here I've got a specified type. It's list of number, right? If I try to make a list of integer and pass it to the method, it doesn't work, right? Generics are not covariant, right? So a list of integer is not substitutable for a list of number, right? But the method should still work, right? The values in a list of integer are also big N numbers, right? Because number is the supertype of integer. So this method here should still work. The problem is specified type parameter here. Right? So how do you get around the problem? Right? You use an upper bounded wildcard. What do you write? Right. So I don't care what the actual type is for my list. I don't care what the elements are. All that I care is that they are a subclass of number. Right. So question mark extends number. Right. And now the same method works whether I pass it in a list of number, a list of integer, a list of double, a list of short. I think it works if you pass it in a list of character. But any numeric type, it now works. Right? So this version works only if you pass it in a list of number. Right? If the user has a list of integer, doesn't work. Right? Notice that the code doesn't change inside the method, right? It would be nice if your code worked for any list, as long as the elements were some subtype of number, right? You can do it that way right there. Right. So using the upper bounded wildcard type makes your method more flexible for you, for the users of your class. Right. If this thing didn't exist, the solution would be to make a separate method for list of double, a separate method for list of integer, a separate method for list of short, and so on and so on and so forth. Right, which kind of defeats the purpose of creating these generic types in the first place. Right. So again, another example of an upper bounded wildcard type. Now you could have written that same method using an extra type parameter. Right. So again, we could have written this as a generic method. Right. Instead of using question mark extends number, write t extends number. Right. Now the method becomes generic. So your type now appears in front of the return value. Right. But again, that type t never shows up in the method itself. So it's cleaner, at least as far as the designers of the language are concerned, if you use the question mark instead. Okay, so still talking about upper bounded wildcard types, right? An upper bounded wildcard type restricts the unknown type to be, right? It's either the exact same type as the upper bound, so it's either exactly number, right? Or it's a subtype or any descendant type of the upper bound. Right, so any type that is a descendant of number. Oops, sorry. Okay, so upper bounded wildcards are useful when the variable is a source of data. Right, so what the heck does that mean? So remember, we had this pop all method in our stacks class. Right, pops all the elements out of a stack and adds them to a collection. Right, so the stack in this case is our source of data. Right, the elements are coming out of a stack or coming from a stack. So that pop all method, we can make it even more usable than it is if we used an upper bounded wildcard instead. So here's pop all, right? So the original implementation, we had a stack of some element type t and a collection who has the exact same type t. Right? So we have a stack of integer, we can add it to a list of integer, right? However, if we have a stack of number, we can't add those to if we have a stack of integer, we can't add it to a collection of number. That doesn't work, right? Because the types are different. So that's no good. So what we really want in this case, right, is that the source type t, we really want it to be a subclass or a descendant type of the collection type here. Right. So what we really want to write is that the element in the stack can be any type, right, as long as it is a subtype of t. Right. So in other words, if collection is a collection of number, then we ought to be able to take a stack of double and push the element and take the elements out of the stack and add it to the collection. If you write it this way, then you force the user to have the exact same type in their stack as in their collection. Writing it this way makes your method more flexible, right? As long as that type is a subtype of t, right? This method still works. The code doesn't change, right? The only thing that changes is your specification of the generic type, right? And so when you take into consideration inheritance and generics, right, you end up with funny looking code that looks like this, right? And now if you go back and look at the collections class and you look at the methods there, they start to make sense, right? A lot of the methods there look like something question mark extends something, right? The reason they look like this is to provide the maximum amount of flexibility for the users of the class. Right. Now, there's also lower bounded wildcard types. Okay, so an upper bounded wildcard type, let's go back quickly, restricts the unknown type to be a subtype of the upper bound. Right. There are cases where you want your type to be a superclass of the other thing. So that's a lower bounded wildcard. Right. So a lower bounded wildcard restricts the unknown type to be the same type as the lower bound or any supertype of the lower bound. Right. So if you want to specify a lower bounded wildcard, you use the keyword super. So again, the language recycles an existing keyword, right? And so now the word super means something else, right? So now it's used to indicate you have a lower bounded wildcard. So here's the method add one. So this one takes in a list of integer, right? And all it does is it takes it adds one to every value in the list, right? Oh, sorry. What am I saying? It doesn't add one. Sorry. It adds. Sorry, that's dumb. It adds the integer one to the end of the list. Okay. So that method there would be a lot more flexible if a lower bounded wildcard was used instead, right? So notice here you've got a list of integer, right? I can add a one to that list of integer, right? It would be nice, right, if I could add a one to a list of double as well, right? Or add a one to a list of number or something else. Right? So in this case, it would be a lot more flexible if we used a lower bounded wildcard instead. Right? So here, I don't care what the type of list is, right? As long as that type is a superclass of integer, right? This ought to work, right? So in other words, I ought to be able to add the number one to any list, right? Where the element type was a superclass of integer, right? So if I have a list of number, I should be able to add a one to it. This doesn't work for a list of double. So a list of double is not a double is not the super type of integer. So this doesn't work in this case. Okay, so when are the lower bounded wildcards useful? Bit of time, just about out of time. Okay, so a lower bounded wildcard is useful when the variable is a destination for the data, right? So upper bounded wildcard, useful when you have a variable that's a source, right? Lower bounded wildcards are useful when you have one of your variables is a destination for data. So remember push all. Sorry. Here's the original version of push all, right? We have a collection, our source collection, and we have a destination stack, right? So here the element types must exactly match, right? So if I have a list of integer, this method lets me push those integers onto a stack of integer, right? But if I have a list of integer, right, I ought to be able to push those integers onto a stack of numbers, right? So if I want to relax the constraints on the destination type, right, I can use a wildcard, say super T, right? So I don't care what the element type is for the stack, right? As long as the element type is a super type of T, right? This ought to work, right? Again, the code in the body of the method doesn't change at all, right? But it makes your method more flexible for the users of the method, right? They no longer have to specify a type for the stack. They no longer have to use a stack whose type exactly matches the type of the collection.